Hello, welcome to Chem Cloud. So we'll continue with structure determination from spectral data. This is our session 4. So we'll start with next problem. This is our problem number 6. Deduce the structure of a compound based on given spectral data. So in this problem, elemental analysis is given. So we have a percentage of carbon and hydrogen with us. From this elemental analysis, we need to derive molecular formula. So we will see how to derive molecular formula from elemental analysis. Then in IR, we have 1720, which can be CO stretching, 1650, which can be C double bond C stretching of alkene. Then we have 1185, this can be C single bond O stretching. In H1 NMR, we have 5 peaks. So there must be 5 different groups of proton. So we'll start with this. So elemental analysis, we have a percentage of carbon and hydrogen. So we'll write this 63.2 and 8.8, right? So if this total is not 100, then whatever the remaining percentage will get, that will be the percentage of oxygen. So if you look at this number, 63.2 plus 8.63.2 plus 8.8, this will be 72. So remaining 28% will be oxygen. So assume we have 100 grams of compound. So in that 100 grams of compound, 63.2 grams of carbon, 8.8 grams of hydrogen and 28 grams of oxygen are present, right? So here we will find out moles of these elements. Okay, so how to find out moles? The weight of the compound divided by molecular weight. So in this case, this weight of the element divided by its molecular weight or atomic weight, that will take. So 63.2 divided by 12.0, 8.8 divided by 1.0, 28.0 divided by 16.0, this will take, right? So if you do this, 63.2 divided by 12, it will be 5.26. So I'm writing here 5.26. 8.8 divided by 1 will be 8.8, and 28 divided by 16, this will be 1.75. I'm writing this 1.75. So this is the moles of these elements, right? So I'm writing this as a carbon, hydrogen and oxygen. These are moles of these elements. Now what we'll do is we'll take the smallest number from this and divide by that number to all these numbers, right? So C is 5.26 divided by 1.75, H is 8.8 divided by 1.75, and in case of oxygen, 1.75 divided by 1.75. So if you do this, 5.26 divided by 1.75, so this will come around 3.0. So carbon is C3, and carbon is 3. H for H, 8.8 divided by 1.75, this is coming around 5.02. So we'll take H5, and this will be obviously 1, right? So this is a general formula we have, C3 H5 1. So this is O1, right? So this is indicating ratio of these elements, right? I'm writing this here, C3 H5O, right? Or in general we can write C3N H5N and ON. So for this C3H5O, if you calculate sites of unsaturation, right? So C3, it will be C3H8 for saturated. So if you compare with this, there is deficiency of 3 hydrogen. So 3 divided by 2, it will be 1.5. So site of unsaturation is coming 1.5, right? So it's not possible. So we'll go with the next higher number. Suppose N is 2. So it should be C6H10O2. So for this molecular formula, if you calculate site of unsaturation C6H14, here we have a 10 hydrogen, so there is deficiency of 4 hydrogens. So 4 divided by 2, it should be 2. So site of unsaturations for this is 2. So this can be our molecular formula. This can be our molecular formula. So we'll continue with this. Now in IR we have 1720 centimeter inverse. So we have already discussed, if you have a ketone, it should be 1715 centimeter inverse. If you have aldehyde, it should be 1725 centimeter inverse. And if you have ester, then this is simple ester, it should be 1735 centimeter inverse. If this ester is conjugated, so this carbonyl group, if the carbonyl group is in conjugation with double bond, then this value will be lower. So this may appear around 1720 centimeter inverse. So this can be either ketone, aldehyde, or conjugated ester. Then for 1650, this is C double bond C of alkene, C double bond C stretching of alkene, right? Then 1185, this is C single bond O stretching, C single bond O stretching. So this presence of C single bond O stretching indicates the presence of ester or supports the presence of ester, right? So we can continue with our molecular formula where we have 2 oxygen atoms. Now you see this proton magnetic resonance. In this case, you observe this peak A and peak C. In case of peak A, we have 1.25 3H triplet with J is equal to 6.5 Hz, and here we have 4.15 2H quartet with J is equal to 6.5 Hz. So for this A and C, J values are same, so this two must be coupling with each other, right? So this we can write this as a CH3 CH2. So this CH3 has appeared as a triplet because of this CH2. The CH2 has appeared as a quartet because of this CH3, and chemical shift value for this C is 4.15. So this must be connected with oxygen. So this fragment we can take it as CH3 CH2O, right? Now we'll focus on this B, D and E. 1.85 3H doublet of doublet, 5.85 1H doublet of quartet, 6.95 1H doublet of quartet. So if you see this, this is in the region of alkene. This is in the region of alkene, right? So we'll write first this monosubstituted alkene. I'll explain you for this monosubstituted alkene, right? So for this monosubstituted alkene, see this H and H, these are geminal. This H and this H, these are Cs, and then this H and this H, these are trans, right? So for these three, we will get 3 different J values: J geminal, J Cs and J trans. So J geminal will be around 3 Hz, J Cs will be around 10 Hz, and this J trans can be around 16 Hz. 16 Hz, right? So these all will appear as a doublet of doublet in this case. Now instead of 1H, we have a CH3. So I'm writing this CH3 here, H, C double bond C, H, and this is some substituent, right? So now you assume this CH3 will split into doublet because of this H, and this doublet will further split into doublet because of this H. So this H is geminal. So for that, J value can be around 1 Hz, can be around 1 Hz. And this is Cs with respect to this CH3. So this J value can be around 6 Hz, can be around 6 Hz. So this is matching with this for B. Now you see this 5.85 1H doublet of quartet. So we'll check for this. So we have a J value of 16 Hz and 1 Hz. So this H is coupling with CH3. So we'll get a quartet. J is equal to 1 Hz for that. Then this H is also coupling with this H, which is trans with respect to that. So for that, J value can be 16 Hz. So we'll get doublet of quartet with J value 16 Hz and 1 Hz. So this 5.85 proton is can be this one. Then for this H, we have methyl group in the cis position. So for that J value can be 6 Hertz, and another H is trans. So for that J value can be 16 Hertz. So this H must be this H which has appear at 6.95 ppm, right? So our compound must contain this fragment, right? So we'll write structure here. I have a CH3 H double bond C, one more H and some substituent present. And in the another case, what we have derived, we have O CH2 CH3 from peak A and C in H1 NMR. We have derived this fragment, and from IR it also contains carbonyl group, which is more possibly conjugated ester, right? So this X substituent can be, I'm writing carbonyl here. This can be CO, which is conjugation in conjugation with double bond, which is further connected to oxygen, CO stretching, which has appeared at 1185 centimeter inverse in IR, and this is connected to CH2 CH3, this fragment. So if you connect all these fragments, we'll get this structure. We'll get this structure, right? So you can write all this H1 NMR values here to support that structure. So this structure will match with all the data which is given, right? So it must be this one. Thank you so much.